So, good evening. We have with us tonight Mike Washvill of the Cold War Museum to talk to us about Cold War HF intercept and direction finding antenna, the elephant cage. The Cold War Museum, located in Warrenton, Virginia, was founded in 1996 by John C. Welch and Francis Gary Powers Jr., the son of the CIA U-2 pilot who was shot down over the Soviet Union in 1960. The museum was founded to preserve Cold War history, honor Cold War veterans, and provide continuing education about the Cold War. So, Mike, thanks for joining us tonight, and now it is over to you.
Alex, thank you for the opportunity to present to the Montgomery Amateur Radio Club and to speak about the Cold War Museum and this really classic piece of Cold War signal intelligence technology, the elephant cage antenna. I started out life as an Army electronic warfare and intercept systems repairer in 1980. Although I didn't work on the Flare 9 strategic system, I worked on tactical mobile systems. I've always been fascinated by this antenna. I mean, it's an incredible piece of technology. It's an incredible, massive antenna installation, and it's a Cold War classic. So I've done this presentation for a number of clubs, including the Pentagon Club, and the folks down there, of course, obviously really liked it because it covers a critical military system. So let's get right into the presentation here. I'll go ahead and open up the Flare 9 elephant cage. This particular antenna is located down in Augsburg, just north of Munich in Germany. It was one of 8 antennas built by the Army and the U.S. Air Force during the Cold War. Let's see here if I can get that indexing to index properly. There we go. It is an high-frequency direction finding and intercept antenna covering 2 to 30 megahertz in the HF band. It simultaneously provides high-resolution DF and multiple high-gain beams, in this case, every 7.5 degrees around the compass there. So there's 48 high-gain beams off of this antenna, and omnidirectional receive, all from the same antenna installation at the same time, so different users can use it for different functions. You can get a rough idea of the scale of this antenna by looking at those folks in the foreground there walking in front of this antenna. It is a huge, huge piece of equipment. The first circularly disposed antenna arrays with electronically steerable beams were actually invented by the Germans during World War II. The German Kriegsmarine, the German Navy, built the antenna under the code name Wollenweber, wool weaver. Their antenna was a 400-foot diameter antenna system with 40 cage monopoles in a circle, backed up by a reflector screen, connected to the device known as a goniometer, which did the direction finding beam forming to allow you to create a steerable beam and get direction finding bearings off of incoming radio signals. These are 2 different versions of the German antenna there. Again, you can see the cage monopoles. You can see the reflector screen behind those monopoles. That provides some front to back ratio on those antennas and allows the antenna to only receive looking away from the array there. They connect all of those antennas back to the central receive building with equal length cables. So all the signals arrive at exactly the same phase there. But as radio waves come in and hit the edge of that antenna, they're hitting different antennas in different points in time. So what they do is with the beam forming device, or as the Germans called it, the sine compensator, that provided a way to co-phase multiple antennas together in order to produce a higher gain, very narrow directional beam to give you that direction finding capability for the antenna. Here's the German operator. Their system is completely manual. The operator has to sit there with that large wheel, rotate it around, look at the degree scale on the indicator or the beam former there to figure out exactly what direction that radio signal is coming in from. So he just rotates that around, gets a peak on his indicator meter. That develops a line of bearing at that station. Combine that with lines of bearing from other stations, and you can triangulate the location of the distant transmitter. This is a diagram showing how that beam former works. They use a collection of capacitors and inductors. They're specifically chosen such that as that beam former rotates around, it is capacitively coupled to a group of antennas at a time. The antennas are phased together to ensure that all of the signals from those different antennas arrive at the summing point at exactly the same time to produce a high gain beam. And the fact that that disk with the capacitive coupling rotates around will produce the electronically moving or electronically steerable beam to allow the direction finding to occur. Now, at the end of World War II, we capture or destroy these antenna systems. We seize interesting pieces of technology from the Germans. The Soviets do the same type of thing. We also get some of the technicians and the engineers that were involved in designing these systems. Now, the Soviets, capturing the German technology, basically go out and build 32 copies of this, what they called the Krug, or the wheel antenna, and they build those around the Soviet Union. They're used for direction finding purposes, for signal intelligence, and also because the Soviet Union is 11 time zones wide and they don't have the same sort of density we have to put navigational aids in for aircraft systems across vast expanses of an empty country. They're used to provide long range navigation for commercial and military aircraft. Aircraft could call in, get multiple direction finding bearings from particular stations, and then determine exactly what their position is over the Soviet Union. This is a close-up here. You can see the reflector screen. You can see the cage monopoles on the insulators there. The cage monopoles provide a wider bandwidth antenna than any sort of narrow single conductor type of monopole antenna would do. That gives them the frequency range across multiple octaves of the HF band there. As I said, the US government seizes a lot of this material and equipment, and the US Navy goes out to the University of Illinois at Champaign-Urbana, the electrical engineering department, and in the 1950s sets up a study program to look at developing improvements in direction finding and signal intelligence technology. At Bonneville, Illinois, here you see a picture of the 900-foot diameter experimental station that they built. Now, one of the major things the Navy does with these antennas is, rather than passively just taking the antennas, connecting them directly to the goniometer to do direction finding, the Navy puts a multi-coupler amplifier on each one of those antennas, allowing them to produce multiple copies of the antenna signal in that central electronics building. One copy of the signal from each of the antennas is fed to the goniometer for direction finding. But at the same time, the other copies of the signals can be used to create fixed high gain beams, combining multiple antennas on a part of the array together to produce high gain directional receive beams without the necessity for having to put up other antennas at your intercept facility there. And they also combine a single copy of every single signal together into an equal weight device, the omnidirectional coupler, to provide omnidirectional reception capability. So for general purpose HF search, you might be on the omni setting. You'd listen to signals coming from anywhere. If you use the goniometer, you could do direction finding and identify a particular target signal of interest. I want to listen to Moscow, I want to listen to Havana, Cuba, but I want to ignore other parts of the compass. I could then connect receivers specifically to those fixed high gain beams, so specific operators could listen to particular targets, concentrate on them, while other operators are busy using the same antenna array to do high resolution direction finding. In the late 1950s, right here in the Washington, D.C. area, just south of Alexandria, Virginia, in a place called Huntley Meadows Park, the Naval Research Lab builds a 400-foot diameter experimental antenna system. They experiment with different types of antennas as the actual active elements of the receive system. Half rhombic antennas, stuck basically little small triangles that were built with a single suspension mast in the middle and then fixed down at the ground on either end. They put those in a circular array. They tried 40 sleeve monopole antennas without the reflector screen, and then 40 sleeve monopole antennas with the reflector screen. The rhombic antennas didn't work very well. They wouldn't discriminate between horizontally and vertically polarized signals. Having the sleeve monopoles without the reflector did not provide the sufficient level of front to back ratio for the high gain reception beams. So they settled on a design utilizing the reflector screen, sleeve monopoles in a circle outside the reflector screen to give them the front to back ratio they need, to give them the DF resolution they need. That 400-foot antenna was installed down there about 1957 and used by the Naval Research Lab for a number of years. In fact, there's a photo of the reflector screen. The monopole antennas are about 40 feet tall, are the little white sticks that are around there in front of the reflector screen, and it all goes to the central receive building in the middle. This is a view from the ground level showing you the antenna array, the screen array, a close-up of those sleeve monopoles, and it looks like for that prototype, they just bought some pieces of corrugated drain pipe and made those supports on the bottom of the monopoles with corrugated drainage pipe there. But again, it was an experimental antenna. It wasn't a permanent design. This is another picture of Huntley Meadows. The new circularly disposed antenna array, 400 feet in diameter, is located on the left side of the photo. On the right side of the photo, there are two separate antennas of what is known as a GRD 6-direction finder. It's got a low band and a high band array. Each one of those is a separate array that's an 8 vertical antennas in a circle, and known as a U-Adcock array. And that was the Navy's previous DF system, but it requires a lot more real estate because you look at it there, you've got those several hundred-foot diameter ground screens in the individual antenna arrays, and they have to be separated hundreds of feet apart to avoid interaction. So the CDAA actually provides a more compact receive system with higher capabilities. The Navy takes their design from both Bonneville, Illinois, from the University of Illinois project there, and from the NRL antenna, and design an antenna known as the FRD-10. They build 16 of these systems around the world. You've got 2 reflector screens, you've got 2 rings of antenna elements, you've got 42 to 9 megahertz folded monopole antennas, and then around the outside, a smaller reflector screen with 120 antenna elements covering the 9 to 32 megahertz range. These antenna systems they build are about 900 feet in diameter. There's a picture of the antenna that used to be installed out at Coronado, California at Imperial Beach. The building in the middle not only houses the electronics that do the combination of the antennas, the beamforming and such, but that's also where the Intercept facility is. So you've got the Intercept operators working inside there. You can see the parking lot with the cars around there. It is a large antenna array. Speaking of those beams, the Navy antenna produced 30 high gain beams by combining 10 antennas at a time. You can see from this diagram, each of those radial bearings every 12 degrees around the compass. They combine a group of antennas together, phase them together. That produces those high gain beams for both the low band antenna on the inside and the high band antenna array on the outside. Again, this antenna provides simultaneous omnidirectional reception, directional high gain reception, and high resolution DF capability in one antenna at the same time, multiple functions. Now, out at the radio quiet zone, there is a Navy facility that was part of the Naval Security Group, the Naval Signal Intelligence Branch, known as Sugar Grove, West Virginia. They installed 2 of these FRD-10 antennas on there. However, they were not used for intelligence purposes. What happens is in the 1940s and 50s, they established Naval Comm Station Cheltenham in Cheltenham, Maryland, just south of Andrews Air Force Base. Yeah. But by the late 1960s, the noise level in the DC area was getting so high that that became a less than desirable HF receive facility. As a result, in about 1968, 1969, they install a pair of these antennas at Sugar Grove. They don't put the goniometer in there for direction finding, but they use them to produce those high gain directional beams. The fact that these 2 antennas are spaced about 1,500 feet apart allows you to do diversity reception, where 2 receivers would operate on each channel at a time. And as the signal might fade at one antenna, the fading at the other antenna might be uncorrelated with that. And by averaging the signal between the 2 antennas, you get a higher, more consistent signal level and avoid some of the HF fading that occurs on skywave communications. The Army and the Navy, or the Army and the Air Force, on the other hand, decide on a different design for an antenna, the FLR-9. This is the antenna that was installed at Field Station Misawa in the North Island of Japan. It was torn down eventually in 2005, but it was put in there, operated by the Air Force, but also staffed with Navy and Army personnel and a large number of NSA, National Security Agency personnel. And that was part of the worldwide network that NSA ran in conjunction with the services to do signal intelligence. The Air Force builds 6 of these antennas: RAF Chicksands, San Vito Air Base in Brindisi, Italy, Field Station Massawa, Clark Air Force Base in the Philippines, Elmendorf, and Karamarsul in Turkey. The Army builds 2 of these antennas: one, Field Station Augsburg, down near Munich, and the 7th Radio Research Unit in Udon, Thailand in 1970. So there are 8 of these antennas, 4 in the European theater, 4 in the Pacific theater, providing that signal intelligence collection, direction finding, processing for the Air Force and for the Army in conjunction with NSA. As I said, you've got omnidirectional receive coverage. You get 48 15 dB gain beam antennas or beam patterns every 7.5 degrees around the compass. You have sector beams, which are much wider beam width, roughly 90 degrees or so, lower gain, but they cover a larger area and angle, so they can cover a more widely distributed group of signals. And you also get fractional degree accuracy, high resolution direction finding. A typical HF-DF antenna with a short baseline, you're talking 20 to 50 feet between elements, might have 3 to 5 degrees worth of variation in the line of bearing there from the actual signals coming in. With this antenna being roughly 1,200 feet in diameter and your effective antenna array being 1,200 feet in diameter, your DF accuracy improves to a fraction of a degree in the HF band there. The operational detection range of these antennas was typically rated at about 4,000 nautical miles, which is roughly 4,600 statute miles. You've got 3 rings of antennas: an outer ring, the A band, 48 elements that are the vertical sleeve monopoles. They cover 2 to 6 megs. You've got 96 of the band B, 6 to 18 monopoles on the outside ring there, spaced behind and between the band A antennas. And then inside, there are 96 what they call bow tie dipoles on the inner reflector, providing coverage in the 18 to 30 meg band. So you've got complete coverage from 2 to 30 megahertz between the 3 subbands on this antenna. There's a picture of the antenna out at Elmendorf Air Force Base in Alaska. You can see the antenna array, the outside reflector ring. You can see the 2 rows of antennas from their little shadows there. The inside ring, which is roughly 300 feet in diameter. The white circle in the middle is a 90-foot diameter building known as the roundhouse, where all the electronics and beamformers are. And then off to the right, you'll see the operations building there and the parking lot with the cars. You really do get an idea of exactly how big this thing is. This is a side view of 1/2 of the array, starting at the center on the right. You've got the outside sleeve monopoles on A band. They're 105 feet tall. You've got those 96 band B sleeve monopoles that are 35 feet tall, 121-foot tall reflector screen. Then inside, you've got the ring, the 300-foot diameter ring of the C band antennas with the standoffs holding those bow tie dipoles there. So there's a total of 192 separate antenna elements in this array. You really have to appreciate an antenna that's the size of the Pentagon. This thing is 600 feet from the middle of the roundhouse out to the outside where one of those antenna elements is. And from the Ground Zero Cafe in the middle of the Pentagon courtyard, it's roughly 605 feet out, 610 feet out to the outside wall on the E-ring of the Pentagon. The thing is, the Flare 9 is actually 50 feet taller than the Pentagon, because the Pentagon's only 71 feet tall. So it is a huge antenna. From the ground, you see the outside ring of the giant gray A-band monopoles, the smaller ring of the white B-band monopoles, and then that large reflector screen, which consists of wooden towers and wooden supports holding vertical wires that produce an HF reflector to eliminate signals coming from the right, for example, in this case, and provide a little bit of extra gain for the monopoles receiving signals from the left there. This is another view at Field Station Massawa in 2005 when they started the demolition project. Again, you get an idea of the size and scope and scale of this antenna. It is massive. These sleeve monopoles are kind of interesting. They're basically a grounded tube and then a monopole antenna sticking out of the top of it. Effectively, it's like a piece of coax where you've got the grounded shield going up, and then you've got a large piece of wire coming off there, the center conductor coming out. Because it's not a small diameter monopole connected directly on a ground plane or counterpoise, it's got a much wider bandwidth than just a single monopole element mounted directly against a ground screen. The bandwidth on the antennas here, 2 to 6 megs, 6 to 18 megs, is roughly 3 to 1 versus typical narrowband bandwidth you have on a normal monopole antenna. There's a schematic view of exactly what those antennas consist of: the grounded tube, the feed line, and a matching stub. And then you've got the actual insulator at the top, and you've got the element sticking out there on the top. That's the B band. That's that 300-foot diameter cage that holds those bow tie dipoles up there vertically. And that antenna is the central antenna that covers the 16 to 30 megahertz range. The bow tie dipoles are highlighted over here on the right. You see the circles. You basically have those rectangular metal frames that come together at the little V feed point there. Because they're large in diameter and they're large in height, they're not small linear elements. They have, again, a bandwidth of roughly 18 to 30 megahertz there. And there is an upper and a lower ring of those that are combined together in the C band 18 to 30 meg range there. They co-phase them together to produce, from those 96 specific antenna elements, 48 actual antenna feeds into the roundhouse. There's a diagram showing the coaxial cable balance that are used to provide the balanced feed. Then the combining network that uses pieces of coax at different impedances to allow it to combine together with a quarter wave transformer to produce a 75 ohm interface while paralleling two of those dipoles together at a time. So it's actually engineering marvel that this whole thing is put together. The other thing that impresses me is the fact that every one of those antenna elements has to go back to that roundhouse with equal length levels of cable. So every A band element has an exact same number, exact distance of coax cable going back to the roundhouse. Every B band element has an exact cut cable, and every C band element. You need to make sure those cable lengths are equal to each other in order to ensure maximum performance of both the direction finding beamformer and the beamformers there. In this array, there are 92,000 feet, 17 and a half miles of 7/8 inch hardline feeding the antenna elements back to the roundhouse. From the roundhouse back to the actual operations building, you have a tunnel that's 1,000 to 2,000 feet long with roughly 160 runs of hardline. I want to be the salesman at Andrew Corporation when that sales call comes in. I need some 7/8 inch 75 ohm hardline. I need to have about somewhere between 50 and 80 miles of this, and I need 8 sites like this. That guy definitely made out on his sales commissions. Here's a picture of Karamersal, Turkey. You can see the ops building in the top center there. You can see where the trench is being done for the tunnel going over to the ops building, and you can see the trenches feeding the cable back to the roundhouse from all of those antenna elements out there on the A band and the B band arrays. That's where that 17 and a half miles of hardline goes. You get omnidirectional receive coverage on this antenna. 48 high gain beams. You've got selectable sector beams that have wider bandwidth there, but cover larger parts of the azimuth. And then you finally have that high resolution direction finding, all from a single antenna array on 40 acres worth of land. I've seen some diagrams before on proposed things for, say, a Navy communication station where they have multiple gain antennas, directional antennas pointing in different directions, plus DF subsystem and everything else. And some of those naval comm stations had up to a square mile of antenna array to perform multiple functions at a particular receive site. Here, 40 acres of property, a 1,200, 1,400 foot diameter circle with the ground screen. All of these functions occur in that one compact space. You have 192 antennas coming in there, 48 A band, 96 B band, 48 C band, connected to 192 separate multi-coupler amplifiers that amplify those signals and send them to the omnidirectional couplers, combiners, the beamformers, the sector beamformers, and the goniometer. There are components there for each of those separate subbands for this. It's a lot of electronics, and this is just a small functional diagram showing you the basic concept of A band, B band, C band being connected to the amplifiers, being connected to the beamformers, goniometers, and then eventually feeding the signals over there. It is a massive, massive maintenance operation. And you'll also notice on the left side here, these little things called line filter, the line tuners. Those devices are basically small adjustable length coaxial lines, because try as you may not perfectly phase match every single one of those antennas going out on A band, B band, and C band to get them co-phased. But those line tuners allow you to fine tune the line length to ensure that each one is as close as possible to perfectly phase matched. Inside that roundhouse, there are 8 separate inputs coming in there, where you have 24 cables at a time coming from 24 different antennas, A, B, and C bands in different parts around the radius of that building, coming in towards all the electronics there. You can see the line tuners installed on top of there, little sliders that allow you to do that fine tuning. They do that with a time domain reflectometer in order to align these. That's a diagram of the line tuner showing you basically it acts as a variable delay line, allowing you to move along that inductor and capacitive lump circuit and allow you to electrically adjust the length of the coax combined with the length of the actual hard line to the antenna to closely match individual antennas in phase and in effective cable distance between the antenna and its multicoupler amplifier. Inside the roundhouse, there are rack after rack after rack in a large circle of the beamformers, the power splitters, the cable entrance, cable assemblies, and the preamplifiers there. The roundhouse has 2,700 phase match cable assemblies connecting all of these pieces together, because once you go from an amplifier to a beamformer, those cables have to be matched. You've got the connectors to the goniometers, those cables have to be matched. So there's 2,700 different phase match cables that are anywhere from 18 inches to 50 feet long in there. Again, this is an engineering masterpiece to make this thing work. Omni Combiner just combines all the antennas together, 360-degree reception. The beamformers combine 16 antennas at a time to produce a high gain beam in one direction. They then step one antenna over and combine the next 16 antennas to produce a high gain beam 7.5 degrees off. They move over one antenna, they combine those 16 antennas. And then they've got these wider band monitor beams there. The sector beamformers only combine 3 to 4 antennas at a time together, giving you less gain but a wider beam width. Now, the antenna itself is relatively simple. You have these elements out there, and an incoming radio wave comes in. It strikes the 2 antennas that are closest to the line of bearing first. Then the radio signal travels a distance to the next pair of antennas and the next pair of antennas and so on until that incoming wavefront hits 8 different pairs of antennas. The first pair of antennas closest to the target get the signal first, so you have to delay them the longest. Then you take the distance between that antenna line and the next antenna line, and you have a slightly less length of delay. You have another slightly lower delay, and the last pair of antennas aren't delayed at all. When they're summed together at the summing point, the combination of those delays allow all of the signals to show up in phase at exactly the same time, giving you 16 copies of the incoming radio wave and producing roughly 12 decibels worth of gain. Combined with the 3 dB worth of gain with the reflector screen, that's how that produces that 15 decibels worth of gain on the receive array, combining 12 antennas together at a time, co-phasing them, and the reflector screen, giving you that 15 dB gain. This diagram basically just shows how the beamformer would work. In the bottom, it shows you the number of nanoseconds of delay time that would need to be done. And that allows you, basically, that delay time is the radio wave moves at basically 1 nanosecond per foot. So they just have to measure the distance between the individual pairs of antennas heading towards the center of the antenna array, and then put the appropriate amount of delay in each one of those to produce that gain. They also, if you notice on the top, attenuate the signals out at the edge of the array a little more than they do at the middle of the array to reduce the amount of side lobe radiation. So the pattern gets a little bit tighter there. Now, the old antenna that was built by the Naval Research Lab, what do you need if you need 20 or 30 or 50 feet worth of delay? You just make a printed circuit board trace and you make it really, 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 really long. Then the next pair of antennas are fed in the middle there. They're fed to a slightly shorter collection of PC board trace to come down to the summing point. The third pair of antennas have even less delay, and the last pair of antennas go right down here to here. So they're physically basically putting electrical conductors in the line in order to produce that electrical delay in the beamformer. In the actual production antennas, the Air Force and the Navy used coaxial cable. Figure out what the velocity factor of the cable is. You go ahead and say, I need this many nanoseconds of delay. I know my velocity factor. I cut lengths of cable, phase match them, put them in the beamformer. The Army, on the other hand, took a simpler way of doing this. They just put about 150 inductors, capacitors, and resistors together and produced a highly complex device that would take the pairs of the antennas on the left and delay them through the inductor capacitor combinations and to sum them together there. I wouldn't want to be the guy to have to align 48 of these. This chart shows you what happens as they go along the outside of the antenna array from antenna 1 to antenna 48. Which antennas are connected together in which groups to produce beams number 1, 2, 3, 4, 5 through 22, for example, on a particular band. And they basically have to make sure they keep all this straight when it gets into the roundhouse and they connect to the beamformers. This is a better, sort of easier diagram to see. You have combinations of antennas, and the first beamformer is connected to the first group of antennas. The next beamformer is connected to another subset of antennas offset from the first one, and then the third beamformer is connected to a third group of antennas. So they just combine different groups of antennas together to produce those beams from the outputs of those amplifier pre-select or multicoupler power dividers there. And then they feed that back into the monitor building. The goniometer device, the angle indicating device, is the core of the DF system. You have a rotating disc. The rotating disc either has inductors and capacitors on the end of that disc on the periphery. The antennas feeding in there, the antenna signals are fed to inductors or capacitors on a fixed disc. And as you rotate the rotating disc, it actually couples to a group of, in this case, 16 antennas at a time to then feed into the goniometer's beamformer assembly. As you move that goniometer disc around, you're effectively electronically steering an antenna pattern on a 1,200-foot diameter antenna. And this movement occurs anywhere from 5 to 15 times per second. So it's the equivalent of spinning an antenna that's 1,200 feet wide, 3 revolutions per second, 15 times per second, without having to actually move anything. As I said, in the German antenna, they had a guy with a wheel that sat there and rotated it and watched a meter to look at the signal strength. But in this system, they actually have a motor drive with a device that determines what angle the disc is rotating at, and it allows the DF system to get that collection of 16 antennas at a time through the beamformer on the goniometer to then be fed into the DF processing equipment to produce the direction finding, what they call line of bearing, or LOB. This is a diagram. It's very nice that the Naval Research Lab declassified this document because that's the goniometer device that was used on the Naval Research Lab antenna down in Huntley Meadows. You have the antennas on the right there, or the left there, with the individual antennas, and then on the right you see the individual coupling pads that would be capacitively coupled to the antennas below, producing the beam forming as you rotated that around. Again, the Navy antenna was a prototype, so they were making things real simple, relatively easy in a lab to experiment with. Now, when you produce that high gain beam for reception purposes, you just combine 16 antennas together, you sum them together, and you produce a high gain pattern pointing in one direction. But in the direction finding world, what happens is when you rotate that directional pattern, the directional sum pattern, the combination of all the antennas, is relatively wide. If you take half of the beamformer, the left half, and you take the right half of the beamformer, and you produce 2 separate signals, and you subtract them from each other, you get a null. If that antenna goniometer is pointing directly at the line of bearing, both sides are equal, but they're subtracted from each other. So you get a very, very, very sharp null, which has higher angular resolution than that combined beam pattern. So as a result, When you're doing direction finding, you actually produce a sum signal, the combination of all 16 antennas, and then you produce the difference of the right half and 8 antennas and the left half 8 antennas. You divide the sum by the difference, and that produces a very, very high resolution direction finding pattern. This is, for example, from the Naval Research Lab document from 1957. You see a relatively wide beam pattern up on the top there of the sum beam. And that sum beam, is wide. And yes, if you bisect it, you could roughly estimate what the actual line of bearing is. On the bottom, you see what the difference signal is, these two lobes that go off to the side, but the actual line of bearing is right down the center, the middle of that V. So then, if you take these diagrams here, they divide the sum signal by the difference signal. And when you're dividing a number by a number that quickly approaches zero, you actually get that very, very needle sharp pattern right there, the actual line of bearing. That's the key to making this thing produce that high resolution direction finding. Here's a picture inside the roundhouse from the NSA video up in Elmendorf Air Force Base, the last of the elephant cages that was taken out of service. There's actually a beautiful unclassified video on YouTube you can watch. They fly a drone through this thing. You get an idea of exactly how big it is and how impressive it is. That is one of the two of the three goniometers inside that roundhouse there. You can see the coaxial cables coming in, bringing in the 48 antennas in, the rotating disc assembly and the beamformer in the top. That is the device that actually does the direction finding. There's one for each of the bands in the antenna system. They've got one of those on display down at San Antonio at the 25th Air Force now, what used to be the Air Force Security Service, Electronic Security Command, the Signal Intelligence branch of the Air Force. They have one of those up at NSA at the museum, but unfortunately it's in the warehouse. They have not put it on display yet. That particular one came out of the San Vito Air Base down in Brindisi. Now, you've got 48 monitor beams, 6 sector beams, one omnidirectional beam or one omnidirectional pattern, and then a DF signal for each of 3 different bands. There's 160 signals there total. Depending on where that operations building is, 1,000 or 2,000 feet away from the roundhouse, you got a tunnel taking all these cables back. It basically totals out to anywhere between 27 and 54 miles, again, of 7/8 inch hardline to connect this antenna. That's a picture of the tunnel. Every one of those cables is that 7/8 inch HELIAC 75 ohm low loss hardline going back from the roundhouse over to the ops building. And at the other end of the line, there's a little bit of a patch panel in there because there's a lot of users using these signals for a lot of different purposes. So that again is a picture from inside one of the facilities around the world there, giving you an idea of the scale of both the signals coming in and the number of operator positions and number of intelligence collection systems that are depending on this antenna there. Here's a picture of one of the early generation DF consoles. You could sit there at a RAF Chicksands, for example, in Great Britain, and an Air Force officer could sit there and push a button, do a DF line of bearing on a target, say in East Germany. At the same time, DF commands go out to Brindisi Air Force Base in Italy, down to Field Station Augsburg, and down to Karamursel, Turkey. Those DF cuts come back. You now have a 1,400-mile baseline. The direction finding signals from those 4 individual stations converge together, and on your screen, you'll get an indication of exactly the location of that target, while at the same time, an Army operator down in Augsburg could be doing a DF mission, press a button, get DF cuts again from those 4 stations in Europe, and prosecute his targets that may be in Czechoslovakia or the Soviet Union or Hungary or some other portion of the Iron Curtain there. This is the newer generation. This is probably the mid-1980s. They were just starting to introduce these Raycal R2174 receivers when I was in school at Fort Devens in 1981. So that's probably mid-1980s, and that was the improved DF positions there on the Flare 9 system. The other operators are just sitting there with conventional receivers. These are some Air Force operators. They are voice intercept operators, or they could be doing Morse. They've got their R390 receivers there. They've got some audio tape recorders. This is the kind of thing that would be there. You would just have operators with headphones chasing down enemy signals, doing situation reports, sending reports up to Air Force, Army, Navy, NSA on the intercepts and the intelligence they collected. Some of these other systems, like here, this is a system called TIBO, the Tactical Exploitation of Binary Operation. This was designed for the interception of enemy teletype and data signals. So you've got your R390 receivers, you've got some wideband multi-channel tape recorders, you've got a lot of Model 28 teletypes there that are being used to process, collect, and print out intercepted enemy non-voice communications, teletype, data type communications there. The system built by the Air Force and the Army was referred to as Iron Horse. In Europe, RAF Chicksands, Field Station Augsburg, San Vito Air Base, Karamursel in Turkey, a 1,400-mile baseline. With a reception range of 4,600 miles, basically those four stations covered 2/3 of the Soviet Union, all of Eastern Europe there. In the Pacific, you've got Elmendorf Air Force Base in Alaska, Field Station Misawa in Japan, and Clark Air Force Base in the Philippines, and Warrenton in Thailand, again covering basically 2/3 of the Soviet Union plus all of communist China there. So by the 1960s, we've got the world ringed with those antennas. The Navy has got 16 antennas all over the world because they've got to cover every ocean on the planet. So their target space was actually larger. They had a larger number of antennas in the Navy's Bullseye, Classic Bullseye program, which was their code name for their DF subsystem around the world. What happened to these things? Karamursel, we left in 1977, especially after the problem with Turkey and Greece over the island of Cyprus there. We removed the vital components out of there, including the goniometers. The station was eventually demolished in the 90s. After the Vietnam War ends, we shut down Udon, Thailand, 1976. Clark Air Force Base in the Philippines was abandoned in 1991 after Mount Pinatubo when we lost our basing rights. RAF Chicksands is torn down in 96. San Vito is shut down, eventually demolished. Misawa is demolished. Augsburg was turned over to the Germans in 1993. I think the antenna is still there. And finally, Elmendorf gets shut down in 2016. It is still there. They're not using it actively for intelligence collection, but it still physically exists there. You can see, for example, Field Station Augsburg, that, again, the antenna array is still in place there. At RAF Chicksands, you can see the 1,200-foot diameter ring where the towers were that held all of the reflector screen there. You can see the little base pads for that, but that's the only thing left there in Great Britain. In the Philippines, on the other hand, they got a little bit creative. They kept some of the monopoles and they used them as decorative flagpoles. And they took the support frame that held up the reflector screens and the C-band antennas, and they used that to support a fabric roof and created an outdoor amphitheater, kind of like Wolf Trap Center for the Performing Arts, and turned it into a theater complex there. So they got kind of creative with reusing it. Why did we shut these things down? First off, there's a lot less HF communications that we need to do SIGINT on. It's no longer the predominant long-distance military communications mechanism for strategic and long-range communications. It exists in some form, but nowhere near the volume it did during the 1960s, 70s, and 80s. The other thing is there's 240 separate antenna elements in that array, 192 separate sets of feed line with 192 phase and amplitude matched amplifiers that all have to be aligned, all have to be monitored. They put solid state amplifiers in to replace the original tube stuff. It got a little better, but still, it required a whole lot of work and maintenance. And it's a massive antenna structure. And if you watch the last Elephant Cage movie, you actually see the frames of all of that stuff, that 1,100-foot diameter ring of the reflector screens and the 300-foot diameter screen in the middle there holding up the C-band elements. It's all unpainted wood like a giant old roller coaster. It wasn't really intended to last 50 or 60 years, so it wasn't worth the trouble. In the contemporary environment, use of modern digital signal processing, use of interferometer type DF techniques like they do with the FCC, for example. They use a triple channel interferometer where they put up basically 9 separate digital receive antennas in 4 sets of equilateral triangles. They digitally process the signals. They can extract DF information from that. They can automatically and digitally calibrate and compensate for performance variations in the thing without having to do all the physical work necessary to keep one of these old antennas alive and running. But the concept is still valid. And in fact, this TCI Corporation, which makes a lot of intercept equipment and signal intelligence equipment has proposals for use of, in this case, a large number of wire, what they call log periodic wideband arrays, connected in a circle, connected to beamformers to produce a circularly disposed antenna array. You combine that with modern digital processing receivers, software defined receivers, the ability to process potentially the entire HF band and simultaneously monitor basically 2 to 30 megahertz continuously and automatically track and produce DF information from all the signals visible on HF at one time. I mean, that's the kind of horsepower that's available in the digital realm these days. So, anyway, that is the story of the Flare 9 elephant cage, circularly disposed antenna arrays, and probably one of the preeminent pieces of iconic Cold War military and intelligence technology. Any questions?
I'd like to make a comment if you hear me.
Yes.
It brings back memories. I was stationed at Karamazov, Turkey in the late 60s. I used the Flare 9. Also, I've been to most of the Flare 9 and Flare 10 sites over my career. I spent about 40 years at NSA. So it was certainly interesting to me. Thank you very much.
Thank you. Thank you. I like that. When I did this presentation for the Pentagon Club, Frank Donovan, W3LPL, goes, hey, I've seen these antennas. I helped improve all of those antennas around the world. So I like getting positive feedback from somebody that was in the business.
Yeah, Frank is a close friend. He lives very close to me. So him and I get together regularly. So he's a good guy. Thank you.
Thanks. Any other questions?
Yeah, Tom?
I have a comment. Came out of basic training, was sent up to Keesler Air Force Base, and then out of Keesler to Griffiths in upstate New York. And we were waiting to get our orders for one of these stations, but I was in power production, not radio, because each of those stations was capable redundantly of producing all their own power. And all of us were praying endlessly not to get Turkey. Because something you may not have learned is the Spetsnaz, the special forces of the Soviet Union, regularly use some of the Turkey substations as their final exercise for Spetsnaz units in training. And the objective was to totally obliterate the station during their business and kill every one of us they could. Now, the nice thing about that is the Air Force identified the pattern and had, on the last time they tried that, they had 140 82nd Airborne troops right at the base and something like 2,000 around it, dug in and waiting for them, and they chewed them up good, and that put a stop to that.
When I went into the Army in 1980, I was originally supposed to go to Field Station Sinop on the Black Sea in Turkey. But luckily, when I was at Fort Devens in school learning electronic warfare systems repair, one of the other students had actually been an Army brat, and he had grown up in Germany and didn't want to go back. So I went to Bavaria to the 1st Armored Division, 501st MI Battalion, and later Vint Hill Farm Station, where the museum is now, and he went to Turkey. So yeah, I'm sure I probably didn't miss anything there with that.
Okay, Rich?
Yeah, hi. Great presentation. I've seen this material before. Were you at the Innovation of Flight Soars Together?
I was actually at we were at Dulles Airport this summer.
Yeah,
when
in
they had
June.
the flight event there, and they were talking about Vint Hill Farm Station. And what we were talking about then was World War II and Vint Hill's role in the lead up to D-Day by
Yeah,
intercepting the Japanese ambassador, and
right.
it starts Operation Fortitude.
Yeah, I met you there. I'm a member of the Smithsonian Amateur Radio Group, and we were right next to you.
Yeah, well, Mike actually is the one that invited us out to the event there because he was at the museum, and he goes, "Hey, we're having this event about World War II. Could you come and present for there, or at least set up a booth for that and talk about stuff. So we did.
Yeah. So I met you there, and we had a good talk and stuff. I'm glad you came to our group too, and gave this presentation. It's very fascinating. It's really a good talk.
This is one I do two presentations for the museum to promote the museum, and one of them is Vint Hill and D-Day and how the road to D-Day starts in November of 43 in Fauquier County, Virginia, of all places. And another one on how you have 4 families of Cold War military technology that make your cell phone work. Narrowband digital voice, spread spectrum modulation, direct sequence. You've got GPS and you've got the internet, all products of the Cold War in your hand. I can do those for any audience. This, on the other hand, my presentation on digital voice communications, I can only do for hams, engineers, SIGINT people, because there's no way to make it non-technical.
Yeah. Well, very good. I'm glad you came.
All right. Well, thanks for inviting me. I mean, Alex, I really appreciate the opportunity to come and, spread some information about the museum and also, just help to educate people on a really fascinating piece of technological history.
Well, we enjoyed having you. Everybody, I mean, it was a great presentation, and I'm seeing those little virtual applause happening because everybody really enjoyed it. Thank you so much. It's incredible what we've done in the past, and it's just a marvel. So thank you.
Well, when I do the digital voice presentation, what I really like to point out to people that digital voice is a brand new cutting edge state of the art technology because they didn't invent it till the 1940s. And I would point that out to people. They go, what? And I go, yeah, there's a secret history of digital voice that was mostly invisible, but it actually started back all the way in the 40s.
Yeah. Well, we'll have to have you back for that.
Yep.
Then. Okay. Thank you. All right. So with that, and once again, thank you, Mike. I think we're done for the evening. Does anybody want to make a motion to adjourn?
So moved.